All right, let's get started. So first of all, don't forget our due of homework 5 is this Friday. So if you haven't started or have any problem, just do not forget to leverage the office hours. And also our final exam is I think next Thursday, right? It's December 15th. And we stick to the previous schedule that we're gonna have this online. So everyone will be convenient, will be safer. And also online exams are usually easier. But I'll keep posting the reminders in the Canvas in case that you do not miss the online exam in Canvas. Okay. Okay. So the schedule, I think this is second last lecture, and then on this Thursday will be the last lecture, right? So the second last lecture today, we're going to talk about the naive Bayes classifier, which is another instance of Bayesian learning. Okay, and then on Thursday, we'll first give some general advice about how to apply machine learning methods in practice, give you some hint about practical usage of machine learning. Then we'll give a quick review of the final exam. I will not talk about what's the details. I will just talk about the requirement and also some suggestions how to prepare a final exam, and give some kind of guidance. Yeah, that's our plan. Okay. So in the last lecture, before the PyTorch tutorial, we talked about logistic regression, right? An instance of the first instance of Bayesian learning. So we talk about two notions of Bayesian learning, right? One is to learn probabilistic concept that you map the instance to a number between 0 and 1, right? So that means you're not map X to be 0 or to be 1. That means the classification. You're mapping it to some probability. So actually you want to predict the probability that the label of X is 1, right? So this is called logistic regression. And we can just use, gradient descent, and we do the maximal likelihood estimation. After some kind of simplification, we see that it is actually consistent with loss minimization, right? Logistic loss, right? And today we're going to talk about another instance. It's called naive Bayes classifier, right? We're going to first introduce the definition or the formulation of naive Bayes. And then we're going to talk about how to learn naive Bayes classifiers. We will only give the details about the maximal likelihood estimation. If you want to do the map estimation, is actually a straightforward extension. Okay. So naive Bayes classifier, right? So what is naive Bayes classifier? So remember when we talk about the logistic regression, right? Actually, we're modeling the probability that your Y takes 0 or 1, right? Or perhaps -1 or 1, sorry. Maybe I use -1 or 1 is more appropriate, given the training or input X, right? So it's a conditional probability. So we model this as, it's a sigmoid function, right? Or sigmoid activation function. And the score is just W transpose X. And here X is augmented with feature 1, W is augmented with bias parameter B, right? And then we multiply this score with Y, right? So that basically says if Y is 1, then this probability is just the sigmoid W transpose X. Is Y is -1, then it is just 1 minus sigmoid W transpose X, right? So this is just a simple form which kind of summarize the two cases together. Right? So everyone is good, right? It's just a review what we're going to discuss. Right? So from logistic regression, we can see that we're actually modeling the conditional probability, namely given X, right? Given the input, what is the probability distribution of your label Y? Right? That's one way of that, right? So now, why not we think about another idea, right? So why should we ignore X? Right? What if we build up a model? We model the joint probability of X and Y. This is another strategy, right? Like, logistic regression, well, we do not care about the X. We do not care about how X is generated, right? We're assuming X is given. We condition on X, we model the probability that Y takes -1 or 1. Right? But here, we're talking about another idea. Like, we try to jointly model the input X and the label Y. Right? So, and it seems that because we incorporate additional modeling over the input X, so you can kind of leverage more information. Right? So naive-Bayes classifier is trying to do this. Right? But you see that there's no free lunch. If you want to model the input vector X, you have some other challenges, so that you need to simplify some kind of assumption to make this easier. Okay, so that's the general idea, right? So that is, we're going to model the joint probability of your input feature vector X and output label Y, right? So if we want to predict the label Y given some observed input X, what can we do? We can just use Bayes rule, right? So remember, when we do the prediction, right, we do not know Y, right? But we have just observed the input features, right? So naturally, we want to know, okay, given this input features, right, what is the probability that the label Y takes different values, right? On 1 or -1, right? So this conditional probability or posterior probability can be computed using Bayes rule, right? So we know that it is equal to the fraction, right? The numerator is the prior probability of your label Y takes some particular label, right? And then the likelihood that given your label takes this particular value, you observe the data X, right? So this is a joint probability, then divided by the marginal probability you observe the data X, right? This is just the application of Bayes rule. So of course, for different choice of Y value, right? Like -1 or 1, if you have multi-classes, you might have 0, 1, 2, 3, 4, and so on, right? So you can use Bayes rule to compute the probability that conditional or given you observed input X, what is the probability you take this specific label, right? And then finally, when we decide our prediction, we can just pick up the label, the particular label who gives the largest posterior probability, right? Does it make sense? Right? You got, for binary classification, your Y might be 0 and 1, right? Then you just calculate, given your data X, right? The posterior probability your label is 1. And then you calculate, given the data X, your posterior probability that your label takes 0. Then just pick up the label who gives the largest posterior probability, right? Does it make sense? Any question? Okay. So, and further, we observe that actually, if we want to maximize the posterior probability, right, it actually has nothing to do with the denominator, because denominator is just a marginal probability of the data, marginal distribution of data, actually doesn't contain y, it's constant to y, and this guy is positive. So that means if you want to make prediction, you can just maximize the prior probability of your label, right? And then the conditional probability that given you take a particular label, what is the likelihood you observe the input data X, right? So yeah, the structure is as follows, right? When we do the prediction of the label Y given some input vector, input feature vector X, right? We just maximize the product where one term in the product is the prior probability of the label being that Y, being a particular label Y, 0 or 1, right? And the other term is the likelihood of observing this input X when you take this label small y. Okay. So, and then, you know that we can see that like in the prediction step, we just need these two probabilities, right? So that means the training, we need to estimate or learn these two sets of probabilities. Okay. Let us look at a particular example. Like we're going to use the tennis example again. Like we're going to revisit that example, right? When we talk about decision tree. So basically, it's a task that according to the weather conditions, I decide whether I'm gonna go out to play tennis or just stay at home. Right? It's a binary classification problem, and then you can imagine that if we use this kind of framework, modeling the joint probability of feature and the label, right? We first need to have the prior probability of the label. In this case, it will be whether I'm going to play tennis or not, right? So suppose this is our prior probability that without observing any data, right, without any information, my prior probability that I'm going to play tennis is just 0.3, and just I will stay at home has the chance 0.7. Right? And then to do the prediction, right, we need to have the probabilities that given my decision, like yes or no, play tennis outside or stay at home, right? What is the probability that you observe different temperature and wind, right? So here we assume that we have two features, temperature and wind, right? So temperature might take two values, just hot and cold, and wind takes two values, like strong and weak, right? So we actually have two tables, right? One table is that, okay, given play tennis is yes, meaning that my label takes value 1, takes 1, right? What is probability that your temperature and wind take different values, right? You actually have 4 combinations, right? 4 combinations. So you assign probabilities. If you can add them together, it will just give 1, right? And similarly, we also need the probability that given you stay at home, namely label is 0, right? What is the probability the temperature wind take different values, right? Again, we got 4 combinations. Each combination corresponds to a particular probability. Okay? Any question? Okay, so now, given this prior probabilities and likelihood probabilities ready, right? So now suppose someday, like I observe the temperature is hot and the wind is weak, right? How can we use those probabilities to predict should I play tennis or not? Right? Apply the rule we just discussed, right? We just maximize the product of the prior probability, play or not, and the likelihood given the decision of playing outside or not, you have observed the input data, which is hot temperature and weak wind. Okay. Now, which is because we have two possible choices, right? Yes or no. Okay. So just to look at on the different choice, what is the value of the corresponding product, and pick up decision who has the larger product, right? Okay. So we just look at it, right? So we consider if the decision yes, meaning the label is yes, then we just calculate the prior probability is what is here, right? 0.3, and then given play is yes, what is the probability or likelihood you have hot temperature and weak wind? So just look at this table, right? And hot temperature and weak wind is here. So you know that given label is yes, then the likelihood you observe hot temperature and weak wind is 0.4. So you just put it here, right? You multiply 0.4 with 0.3, and you got 0.12. Right? Okay. And then we consider another case where you have decision to be not, right? That means your label is no, right? And then the prior probability that your label is no is 0.7. So that's where it is, right? Then we need to look at, given your label is no, your decision is no, right? What is the likelihood you observe hot temperature and weak wind, right? You just look at the entry in this table, hot temperature and weak wind, which is 0.1, right? So you just multiply 0.1 with 0.7, you give 0.07. So now, which label should we predict? Yes, right? Yeah, we just, because we want to find the label who gives the maximum posterior probability, right? Which obviously is yes, right? So my map prediction is yes, right? So any questions so far? We'll give a concrete example about how to use naive-Bayes classifier. Suppose it's not necessarily naive-Bayes classifier, but any this joint probability classifier. How do we make prediction? Everyone's good, right? Okay. So now let us talk about the learning issue, right? So in this case, we use very simple example to illustrate how do we apply Bayes rule to make prediction, right? But now let us consider how to learn those probabilities. Right? Now I want to look at a little bigger problem, which is consistent with the tennis example we use for decision tree. Right? So we have 4 features: outlook, temperature, humidity, and wind. So you can see that outlook takes 3 possible values: sunny, overcast, raining. Temperature, 3 possible values: hot, medium, cool. Humidity, high, normal, and low. And wind, strong and weak, right? So we want to train a probabilistic model, right? Which consider both the input feature vector, which you have 4 features, right? And also the binary label, right? So that means we need to learn the prior probability of your label. Well, here we still have a binary labels, so your prior probability is just the probability of 1 or 0, right? And then we have to learn the likelihood that given different label, what is the distribution of the feature vector. So now the feature vector is a 4-dimensional vector, right? Because we have 4 features. Right? Everyone's good, right? About the setting. Okay. So now let us count how many parameters should we estimate in order to determine these 2 sets of probabilities, right? So first, to learn the prior probability, the prior distribution of play, right? We just need a single number. Why? Yes, exactly right. It's just the binary label. If you know the prior probability you play, then you know the prior probability you don't play, right? You just subtract 1 by the probability you play, right? So to determine the prior probability, we only need a single number. That's seems easy, right? And then let us look at how to determine the likelihood, right? So determine the likelihood. So we need to know that when condition on the value of the label, right, we got two possible values of the label, yes or no, right? Then what is the probability of the whole feature vector? As we mentioned, we got 4 features, right? That means X is 4-dimensional. And suppose we are given some play value, say positive, right? Then we need a value for each possible assignment of these 4 features, right? Okay. So X1, X2, X3, X4 represent overcast, temperature, humidity, and wind, right? So actually you need to assign a probability over every possible combination of these 4 features values. Okay. So how many combinations do we have? Yeah, we need to just count, right? For the first feature, X1, overcast, we got 3 possible values, right? For the second feature, temperature, we got 3. For the humidity, we got 3, and for the wind, we got 2, right? So basically, you got 3 times 3 times 3 times 2 possible combinations of the 4 features values, right? And to identify the distribution over these 4 features, we need to this many configurations minus 1, right? Why is minus 1? Yeah, I heard that. It's yeah, because the adds up together should be 1, right? It's just a probability, right? You just take different possible configuration setting of these 4 features. The probability, the summation of the probabilities over all possible configurations will be simply 1, right? So that means you only need to determine the total number of possible configurations subtracted 1 this many parameters. But these parameters, this many parameters is still quite large, right? So you can see that 3 by 3 by 3 by 2 is 54, right? 54 minus 1 is 51 parameters, right? Plus these 2 parameters. This is just for play equals to yes, right? Condition on 1 possible value of play, right? And you need to condition on another possible value of play, which is no. So you need to determine another 51 parameters, right? And plus, you got a single number here. So you can see that we only have 14 training examples, but we need to estimate 103 parameters, right? So actually, the model is quite large. Right? Does it make sense? Right. So now let us consider a general case. Suppose we're doing a K-class classification problem. That means there are possibly K labels. Right? So to determine the prior probability, we're going to use K-1 numbers, right? Because the last one is just you can subtract 1 by the summation of all the other probabilities. Right? Then let us consider like you got D features, right? You got D features, and for simplicity, we assume those features are all binary. Right? Then for each particular value of the label, right? So this label could be 1 to K, right? So suppose you are given a particular choice of Y, right? y value, you need to determine a probability distribution over all configurations of these D Bloom features. Right? So how many configurations do we have for these D Bloom features? Any thought? Yes, exactly, right? Oh, sorry, it pops up. Okay, yeah. So you just need to look at how many configurations in total, right? So each feature has two possible values, right? So D features will have 2 to the power of D configurations, right? Again, because the probabilities of all those 2 to the power of D configurations, they must add up to be 1, right? So to determine the probabilities, you need 2 to the power of D minus 1 parameters. Right? However, this is just for one choice of value for the label, right? You need to determine such a probability table for every possible label. So you got K labels, then the total number of parameters will be K multiplying this the 2 to the D minus 1 parameters. Any questions so far? Everyone's comfortable, right? Now I want to ask, what's the problem now? Or do you see any problem here? Everyone feels good? This is a good setting? Why is this a good setting? Yes, yes, exactly right. So you can see that the total number of parameters actually grows exponentially along with the increase of the features, right? So maybe it doesn't matter, like you only have 4 features, right? But this rarely happens in practice. In practice, it's very often that you got 100 features, even 1,000 features, right? Like even you got 100 features, imagine how many parameters you need to learn, 2 to the power of 100, right? You won't be able to ask them, right? Given that you have such a limited number of the training examples, right? So the issue is that if you build up a full model for that, right, you need a lot of data to estimate this many number of parameters. And unfortunately, in practice, the data is often quite sparse. At least it won't grow as quickly as how your model complexity grows. Right? So it's very easy to overfit the data. Right? That's the problem. So let us summarize the challenge to learn a joint probability model. Right. So we need, in general, suppose we have K classes to determine the prior distribution, we need K minus 1 parameters, right? And to determine the parameters of the likelihood, suppose we have D Bloom features, right? We need a value for each possible configuration of all the D features. That means you have a very large number of possible configurations because this is a combinatorial problem, right? So I do have like K times 2 to the power of D minus 1 parameters. You can see that the total number of parameters grows exponentially along with the number of the features, right? So that means you need too much data to estimate this many examples, which is really unrealistic, right? And it's very easy to overfit data, right? And how can we address this problem? Any thought? Yeah, that's the right idea, right? That's the right strategy, right? That is, we don't want to use so many parameters, right? And how do we remove those parameters, or how do we reduce the number of parameters? The answer is simple. we want to simplify the assumption, simplify the structure of the model. Right? How can we simplify the model? Right? We introduce additional assumptions, which we call independent assumptions or conditional independent assumptions. You can see that if we make proper independent assumptions, you can largely reduce the number of parameters that need to be estimated. So let us look at some kind of definition. Like let's review the basic concept, right? Conditional independence. Suppose we got 3 random variables, x, y, and z, right? And we say x is conditionally independent of y given z if we can calculate their conditional joint probability in this way, right? That is, conditional on z, the joint probability of x and y can be decomposed as the product of the conditional probability of x given z and the conditional probability of y given z. Okay. So you can see that is the same definition as the independence, except that you're going to condition on a third random variable z. Okay. And you can also equivalently write it in this way, right? That means condition on z and condition on y, the probability of x is the same, exactly the same as condition on z, as the probability of x only condition on z. Right? It's the same as again, it's the same as definition of independence, except that you're going to condition on a third random variable. So now let us look at how naive Bayes classifier introduces its conditional independence to reduce the model complexity. Right? So we know that if we do not make any assumptions about the distribution of this D attributes, condition on Y, then we're going to require K times 2 to the power of D minus 1 many parameters. Right? That's too large, right? So now, to reduce the number of parameters, right, we'll make additional assumption. That is, we assume all those D features were conditionally independent given the label Y. Okay. So this is called naive Bayes assumption. More specifically, it means that we assume, this is just an assumption. We assume that condition on Y, the joint distribution of these D features, is equal to the product of the conditional probability of each feature given Y. So P of x1 given Y, P of x2 given Y times blah, blah, blah until P of xd given Y. Okay. This is just assumption, model assumption. Right? By using this model assumption, now let us count how many parameters do we need. Right? So if this assumption holds, right? So to determine the parameters of the model, we only need to determine the conditional probability for each single feature, right? Right? And for each single feature, say x1, right? To determine this conditional probability, how many parameters do we need? Remember, x1 is just binary feature, right? If you take y equals to 0, how many feature is determined for px1 given y equals to 0? Two, 1, right? Yeah, because x1 is just binary, right? Suppose y value is given, right? You want to determine a binary variables, a binary features distribution. You only need one parameter. You only need to know what's the chance that this feature takes 1, right? Then the chance the feature takes 0 is just 1 minus that probability, right? And of course, you need to consider like all possible cases of y. That means you have k possible labels. For each possible label, you need to determine the conditional distribution of x1. That means you need k numbers, right, to determine this conditional probability. Right? And similarly, you need k numbers to determine our k parameters to determine p of x2 given y, right? Because x2 is also a binary feature. Right? So that means each single feature, their conditional probability given y, it just needs k parameters, right? So in total, we only need kd parameters because we got d features in total, right? We got kd parameters, right? Does it make sense? Any question? Yeah, that exactly. That's the problem. I mean, naive Bayes is just one model assumption. It doesn't mean like it is the oracle or it is the truth. It's just a model assumption you adopt. And when the assumptions are violated, that's where possibly the naive Bayes doesn't work. I think so. Like, there are some cases this could be true. Like, how should I come out example? Like, like you might see the weather conditions, right? You might see the weather. You have a raining. You got temperature. You got precipitation. You can all kinds of stuff, right? And assumptions that of course, if you don't assume some latent variable like some label y, of course those weather observations are correlated, right? But it's really not bad to assume that, okay, given some hidden state which represent the current weather status, and then those conditional on those weather state, then different observations which reflect different aspects of the state are conditionally independent. Right? So they actually this actually relates to a very fundamental concept in Bayesian learning is called exchangeability. That means a set of random variables, they're not necessarily independent to each other. But if you can assume that their distribution is invariant to different perturbations, then there must exist some latent random variable such that condition on that latent random variable, those variables are conditionally independent. This is a very, very important assumption in Bayesian learning, but it's not the scope of our class. That's why, and the assumption is used very widely. And I do agree that since x1, x2, even condition on y, they're highly correlated, then this assumption is bad or not realistic. I do agree. But oftentimes it works pretty well. Even condition on y, x1, x2 are correlated. Right? Any other question? Yeah, I hope everyone like captures like by incorporating this conditional independence assumption, we kind of largely reduce the number of parameters. Right? So previously, the number of parameters grows exponentially to the number of the features, right? But now it only grows linearly with the number of features. So this, in practice, is not bad. It is usually acceptable. That's why in practice, people will always introduce some kind of conditional independence assumption such that you can reduce the number of parameters so the training is acceptable. It is less likely to overfit data. Okay. So now, let us give some kind of formal definition of naive Bayes classifier, right? So the key assumption of naive Bayes classifier is that we assume features are conditionally independent given the label y, right? And again, if we want to make a prediction, we need two sets of probabilities. One is prior probability that the prior probability we label takes different values, right? And then we need to know for each particular feature vector xj, what is likelihood of xj given y, right? The decision rule is that it's a map estimation, right? We want to maximize the posterior probability of the label y given the data x, which amounts to maximizing the product of the prior probability and the likelihood, and then apply the conditional independent assumption. We know that the likelihood of this D features, right, given a particular label y, is decomposed as the product of the likelihood of each individual feature given the label y. So that's our model definition. Any questions so far? Okay, so now let us look at how to learn the naive Bayes classifier. Right? So we consider some kind of a second notion of Bayesian learning framework, meaning that we want to use some probability criterion to search the hypothesis space, right? So we know that for a particular naive Bayes classifier, right? So your hypothesis actually is defined by two sets of probabilities, like the prior probabilities and also the likelihood probabilities, right? So actually, you can imagine that you have a hypothesis space, right? Each particular, like each point in this hypothesis space represent a hypothesis, right? The hypothesis actually corresponds to this collection of the probabilities. You're essentially searching over this hypothesis space to find out the best hypothesis, right? If you want to use probability criterion to do that, that means, okay, we're gonna assign some prior distribution over this space, right? And then given the data, we want to look at the most probable hypothesis in hypothesis space, which is the ground truth. So here we assume that we have collected data set D, right? We got M examples. Xi, yi means ith example, right? And for notation convenience, right, we use xi to represent ith feature vector, right? And we denote jth feature of the ith example by simply xij. So here x is not bolded. Not bolded just means some scalar. And if we bold a small case selector vector, we usually mean it is a vector. Okay. So as we mentioned, like we want to use a probabilistic criterion to select hypothesis. That means want to maximize. We mentioned that we got two approach to search, right? One is called map estimation. One is called MLE, right? Map estimation just means, okay, I'm gonna assign some prior distribution over the hypothesis space, right? However, if we simply assume each possible hypothesis have the same prior, that means it's uniform prior, then your map estimation amounts to or is reduced to the maximum likelihood estimation because the prior is just a constant for every possible hypothesis, right? So we consider a simpler case where we just use maximum likelihood estimation. That means we just assume a uniform distribution over the hypothesis space. Okay. In other words, the prior of each hypothesis, right, it's just proportional to a constant. Okay. So then we maximize given any hypothesis in the hypothesis space, what is the probability you observe the data? We want to find out a hypothesis who leads to the largest data probability. Does it make sense? Okay. And again, we're going to use this ID assumption. That means we assume every example xi, yi is independent and identically distributed to each other. So that means this is a P of D, right? P of data given the hypothesis can be decomposed as a product of each example xi, yi given a hypothesis. Okay. It's very commonly used assumption. Right? So now let us look at what is the probability, right? What is the h assigned to the pair of xi, yi, right? So this actually corresponds to our naive Bayes classifier, right? Given h, what is the distribution, what is probability that you have seen the example xi and yi? According to our naive Bayes classifier, that means first, given h, we got the prior probability of yi, right? And then given yi and this particular hypothesis, we observe xi. That's this joint probability of xi, yi given h, right? Of course, h, because h, you can imagine it contains that collection of the probabilities. So when you want to say, okay, what is P of yi given h, just look up the corresponding probability in h, right? You know this probability, right? And similarly, given h, you know the conditional probabilities of different choices of yi, condition on that choices of yi, what is the likelihood of different choices of xi, right? You just read out that table in h, you can calculate this conditional probability. Does it make sense? For h here, as I mentioned, we also can assign a prior over h. But here, we just assume this h is uniform. So that means its prior is simply constant. So that's why we mentioned that here, right? You multiply pH, that's just you multiply pH, multiply a constant, right? You only model that, okay, given a particular model h, that means given a particular collection of those probabilities, what is the probability you observe this whole data set? You want to find out among this big hypothesis space, which particular collection of the probabilities will give the largest data probability. Does it make sense? Right. So according to our model, right, given h, you can compute the prior of the label yi, and given the label yi, the likelihood of the feature vector xi. Right? And then for this likelihood, we can apply a naive Bayes assumption. That means we can decompose the likelihood of xi vector by the product of the likelihood of each feature j given yi and given h. It's just naive Bayes classifier. So that's where our whole objective function, right? And of course, we don't want to deal with a product of many probabilities. Right? These are between 0 to 1. If you multiply them all together, it can be just truncate to be 0. So a more numerically stable approach will be, okay, we just take a logarithm and do the maximization, right? So that means we just take a logarithm over this guy, right? So then the product becomes sum, right? So you're maximizing a summation of the log joint probability over m examples, right? For each example, we need to look at the logarithm of the prior, given this particular hypothesis, plus the summation over every feature and the log probability of each feature, each particular feature, given the label yi and h. Okay. So what's the next step? Yeah, gradient descent. But before the gradient descent, what should we determine? We should determine what's the form of this guy, right? How do we set the form of the probability of the prior distribution, prior probability yi, and what is probability of the likelihood of feature xij given yi, right? If we consider binary labels, right? If yi like we need to make a modeling assumption about the functional form of these probability distributions, right? If we consider binary label, then very naturally we're going to model this as a Bernoulli distribution, right? So that means the prior is determined by a probability p, right? Which is the probability that your label is 1. Then once you know this parameter p, then the probability that y is 0 is just 1 minus p. Right? And similarly, let us assume the feature is a binary, right? The feature is binary. That means given a particular value of the label yi, right? Cy is 1 or 0, then the G's feature, its distribution is also Bernoulli. It's a very natural choice. That means we need to assign a parameter which we denote by aj. So aj is the probability that, okay, given y is 1, xj is 1. Right? Then given y is 1, xj is 0, is just 1 minus aj. Right? However, that's not finished because we need to consider every choices of the label y, right? So that means for y is 0, then your probability condition of y is 0, then your distribution of xj amounts to another Bernoulli distribution, right? So you have to assign another parameter for that Bernoulli distribution, which we denote by bj. So basically it says we define that bj is the probability xj takes 1, given that the label is 0. And naturally, xg, the probability that xg is 0 given y is 0 is 1 minus bg. So you can see that actually to determine in this particular case, like binary label, and to determine this likelihood model, right, we actually have 2 parameters, right, aj and bj. Does it make sense? Right? Everyone's comfortable, right? And again, we want to emphasize that H is a collection of probabilities, and here H consists of all the P and all AJs and BJs. Okay? You're essentially searching over H. That means you're essentially searching over P, AJs, and BJs. And of course, those are continuous numbers. So you're searching that means we usually use gradient-based optimization. Right? Optimization essentially is a search procedure. Does it make sense? Yeah, I want to like use this example to give a concrete illustration like how our probability search criterion works. I want to associate with our learning procedure, which you do not necessarily always think about as a simple optimization procedure. Right? All the optimization is essentially a searching procedure. Okay. So now let us write down this guy, right? And as we mentioned, right, we want, because P and AJs and BJs are continuous numbers, of course, we want to be able to take the gradient of those parameters so that we can use gradient-based approach to optimize them, right? That means we need to write down an analytical form for this prior probability and conditional probability. And fortunately, for the Bernoulli distribution, there's a very easy and convenient way to write them out. So first, for the prior distribution, that is P of yi given H, we can write this probability in this form. So the P to the power of the indicator that yi is 1 multiply with 1 minus P to the power the indicator that yi is 0. So here, this square bracket means an indicator function. So the input is, you can view it as some kind of condition, right? If that condition is correct, then the indicator function is 1. Otherwise, the indicator function is 0. So now I want to ask why this Bernoulli distribution can be written this way. Any thoughts? In general, how do you want to write a Bernoulli distribution? If else, right? If you want to write yi, you're gonna use some big bracket, right? Like, okay, when yi is 1, then it is p, right? When yi is 0, is 1 minus p, right? But actually, these two cases can be summarized by one formula, right? You can imagine, like, okay, if your yi takes the value to be 1, then this indicator function is 1, right? Because y is 1 is true, right? And this indicator is 0. So you take the power of 0, right, for this 1 minus p, which will give 1, right? So it will give you overall give you p, right? On the other hand, like, if you take yi equals to 0, right, what will happen? You know that this indicator function will simply be 0, right? And then p to the power of 0 is simply 1, right? And this indicator function is 1, right? Then your result will be just 1 minus p, right? So now it's consistent with this if-else case, right? So this is a very smart way to summarize the two cases together into one formula. The benefit is that if you use one formula to do that, you take a logarithm, right? You just take a logarithm. It's just one form of the log probability, right? You don't need to consider like many cases. So. And then it's very convenient to take the gradient, set gradient to be 0, all kinds of stuff. Okay. And similarly, for this conditional probability, P of xij given yi and given hypothesis, meaning given a particular set of parameters, you can write it in this way. Why is this true? Similar, right? Similar to the case we just discussed for the P, right? But here we just add one more case that you have different choice of yi, right? So you can see that when yi is 1, that means for this guy and this guy, the indicator function will simply be 0, right? Because y is 1, right? Y is 0 is simply false, right? So the indicator function is 1, then it is reduced to this guy, right? And this guy actually, y is 1 is true, then the indicator function is only determined by if xij is 1 or not, right? And it will decide whether you're going to pick aj or 1 minus aj. which is the same as the Bernoulli distribution representation for the prior probability of the label. Right? Does it make sense? And similarly, for yi, is 0. So you see that this indicator function and this indicator function is simply 0. That means these guys are simply 1, right? And then the remaining is just about bj, right? And that actually corresponds to another Bernoulli distribution. And once you got this form, once you got this form, right, you can see that it's just a product, right? Product to the power of something, right? And then you take the logarithm. It's really, really easy, right? You just move the power to the front of the logarithm, right? And then you really have a log aj, log 1 minus aj, log bj, log 1 minus bj, right? Oops. If you take a logarithm over this guy, right, it's very, very simple. Right? Now we can see that by writing the probability Bernoulli distribution, or the probability of Bernoulli distribution in this product form and power form, right? You take a logarithm, it will give you a very simple and convenient form. And then next, we can simply take the gradient of each parameter, right? If you take a gradient with respect to p, right? So you take the gradient with respect to p, you set it to be 0, right? And also you can take gradient with respect to aj, and bj is set to be 0, right? And then you solve that equation that the gradient or partial derivative being 0. Here are the results. We're not gonna show you the result, show you how to do that, because it's really really straightforward. We just want to give you the conclusion. So the optimal p, right, is just the ratio of positive labels in the data. So you see that count yi is 1, just means you just look at all the training examples and look at how many training examples positive, then divided by the total number of positive examples and total number of negative examples is basically the size of trained data, right? So actually p is simply the prior probability of p is simply the ratio of positive examples in data. And what about AJs, right? Remember, AJ is actually the probability that given your label is 1, your J's feature takes 1. Right? So this one is calculated as follows, right? You just look at all positive examples, meaning the examples whose yi's are 1. And among those examples, you look at how many of them whose J's feature is 1. Then you just look at the ratio. Like among all positive, suppose like you got 10 positive examples, right? Among all these 10 positive examples, you got 5 examples whose J's feature is simply 5, right? Then your AJ is 5 over 10. Yeah, very intuitive, right? You just count and look at the ratio. And then similarly, if you want to determine BJ, according to our model, right, it is the conditional probability the xj takes 1, given that the label y is 0. Then the optimal bj is actually the ratio of j's feature takes 1 among all the negative examples. So just look at how many negative examples do you have, and among those negative examples, how many of them have j's feature taken 1. You just look at the ratio. So those are very intuitive, right? That's very that actually is quite interesting. Like you just count them, you feel like natural and right? But you can justify them by using this maximum likelihood estimation principle. Any questions so far? Okay, so now let us use what we have just discussed to learn an naive-Bayes classifier, right? For this tennis example, right? So we got 14 training examples, right? We got 4 features, we got a binary label, right? So first we need to determine the prior probability. So we got positive example and negative examples, right? So as we mentioned, the prior probability for the label takes a particular value is actually the ratio of that value among all the examples. Among all the 14 examples, we got 9 positive examples. So the prior probability is just 9 over 14. And correspondingly, the prior probability for negative label is 5 over 14. Okay. And next, let us look at the conditional probability. Okay. Given the label is positive, what is conditional probability? The overcast takes something, right? O equals to S. Right? Again, just the count ratio, right? Just look at how many positive examples, right? Those are marked as orange, right? And among these positive examples, how many examples whose overcast is sunny, right? We'll have 2. So this conditional probability is just the 2 over 9. Okay. Similarly, we can determine the conditional probability that given positive example, the overcast is raining is 3 over 9 because you have 3 positive examples whose overcast is raining, right? And then the remaining probability will be just 4 over 9, right? We just do it for every feature, and we can obtain all the conditional probabilities. Right? Once we collect or estimate it, once we collect or estimate the prior probabilities and all the conditional probabilities, then given a new input vector about the 4 weather features, we can use our naive-Bayes classifier to predict whether we're going to play outside or not. Right? Any questions so far? Everyone's comfortable? Looks like it's easy, right? Okay. Yeah, that's a naive-Bayes classifier, right? So the learning follows a simple rule, like we just count how often features occur with each label. Then we normalize the count to get a valid probability. Okay? And the priors are just calculated from the fraction of the examples with each label. Right? And those rules generalize to multiple classes, right? Meaning you have k classes, you're doing the same thing. And for each feature, you got not only binary features, you might take multiple values. You still can use the same rule to calculate the conditional probability, that condition on particular label y, and what is the probability that you take feature, take value 1, 2, 3, 4, and so on. And then how do we conduct prediction? We use this learned probabilities. Remember, we have 2 sets of probabilities. One is the prior probabilities, the other is the likelihood probabilities that given any label choice, what is the likelihood of each single feature, right? Then we can just maximize the product between the prior probability and also the likelihood probability over that particular input feature vector. Then we can define, we can find out which label gives the highest product, then it is our prediction. Okay, to summarize, so the key assumption that makes naive-Bayes successful and popular is this conditional independent assumption. Namely, we assume that conditional on the label, all the features are independent to each other. And in this way, we kind of like largely reduce the number of parameters. And number of parameters just linearly grows with the number of features, which is usually acceptable in practice. Right? And then we can use maximum likelihood estimation, right? It's pretty simple, right? Well, just if you just take the gradient and set the gradient to be 0, you see that it's simply count. You just count the ratio of examples under different labels. Right? And when you do the prediction, the principle is maximum a posterior principle because you want to maximize the posterior probability of the label y given the data x. Right? So that amounts to maximize the product of the prior and the likelihood. Any questions so far? Yeah, that's a very good question. So for the continuous feature, you won't have some kind of discrete label, table to represent, right? And then the often choice is that you want to assign some continuous, continuous density, like Gaussian density. Like for example, if xj, we want to know y, right? Say y equals to 1, right? If this guy is continuous, you can assume, okay, it is Gaussian distribution, and it's parameterized by some mean parameter mu j and vg, variance prime vg, right? And of course, this is just for y equals to 1, right? For y equals to 0, you might have another mu g and vg to estimate, right? Other question? Mm-hmm. Yes. 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 So what's your question? So you just want to clarify the training procedure? Oh, the prediction. So the prediction, okay, let me probably let us use. So the prediction is like this, right? So suppose you get one particular input vector, right? You got 4 values of the feature, right? So you need to look at the label play and multiply the feature, like say O, T, H, W, give me a label, right? Play, sorry, right? So of course your label can be 1 or 0. So just look at when your label takes 1, what is this product? Right? When label is 0, what is product? And pick up the one who has the largest product, which essentially is corresponds to the largest posterior probability, because just ignore the marginal probability of the data, right? Right. It doesn't matter because we want to maximize the posterior. It is the same as maximizing the prior multiplying with the likelihood. Any other question? Actually, I'm waiting for questions which was asked by previous students. Anything wrong with the current method? We introduced a very simple approach, right? But don't you think the counting here, like we see that the count is just look at how many positive examples, how many negative examples, and given positive examples, how many of them like J's feature is 1, how many J's feature is 0, right? Is there any issue here? Yeah, we need to store that. Suppose we are able to store that. Yeah. Yeah. let me put it more explicitly. Like you need to count all the values, right? But what if the data is still very sparse? Like what if some count is simple to 0? If some count is simple to 0, then you cannot use that. If some count is simple to 0, some AJs are simple to 0, then you do the multiplication, it will make your whole probability simple to 0, right? You cannot use it. That's not uncommon in practice, especially maybe binary labels is okay, but what if binary features is okay, but what if your feature can take multiple values? It is possible that you even don't observe any feature value in, say, positive class. Like say suppose if you look at positive examples, right? Among these positive examples, no examples whose G's feature is 1. Then your AJ is simply 0, right? That's not acceptable, right? Because when you do the prediction, that part will be simply 0. Okay. So in practice, how do we address that? Another issue is that if the data is, you have so many feature values, right? You have different distance feature values given a limited amount of data. Actually, this ratio is quite rough because maybe you just have like 5 positive examples. Okay. Then your estimate is quite inaccurate because your observation is too few. So now how do we address that problem? In that problem, we need to consider the prior of those parameters. Right? Remember here we assume like H, right? H is uniform, that means P of H is constant, right? H represents the collection of P and AJs, BJs. Right? But if we can set some prior over those P values and AJs and BJs, right? And then we combine them with the maximum likelihood estimation principle to do that, and then you will see that this count will not be simply be the count in the data. It also has some part from the prior distribution. In this way, we can avoid like 0 count. Like even from 0 count, it usually it's just returns to the prior, right? And then at least it won't give you a nonsense prediction result. And also, if your prior is quite informative and even the data is sparse, but when your prior knowledge come in, it kind of can remedy the data sparsity issue. And that's why in practice, people won't directly use MLE estimation. They always add some prior to avoid such kind of problems. Okay, let's stop here and see you on Thursday.